So hello everybody, we are back with the lecture number 2 on the topic light. If I and you correctly recall, then in the last lecture we learned about the image formation by plane mirror. We also learned about the types of images, real image, virtual image, right? And the image formation came out to be pretty amazing by a plane mirror. So today what we are supposed to learn? Today we'll be learning about spherical mirrors and how do they form the image, right? The ray diagrams, how do we draw it? And not to forget, the entire lecture will have the use of the law of reflection. Even though the mirror is spherical, we still will follow the law of reflection. You would have to draw a normal, you would have to draw incident ray and then reflected ray. They must make the same angle. So plane mirror, as we learned last time, how amazing it was. Plane mirror forms the image of same size, doing everything similar as what the normal uh, object is doing. The image does the same. If you walk by a certain distance, the image walks by the same distance. And we saw that the reason for that is the formation of virtual image, right? A plane mirror forms a virtual image. So from the object, the rays fall in the mirror, reflect, the second ray falls, that also reflects, and you extend them back because your mind perceives as if it's coming from behind the mirror. And that causes it to appear an image behind the mirror. Now moving ahead, today when we are talking about spherical mirror, there are many parts to spherical mirror. First of all, why it is called a spherical mirror. So it's called a spherical mirror because it's made out of a sphere. How it is made out of a sphere? Well, what we do is we take a spherical metallic sphere and we polish one side of the metallic sphere. We keep on polishing, although you can see your face in a normal metallic sphere also, right? But we keep on polishing it so much and so much that finally it becomes a mirror. It's also an amazing process to learn how mirrors are made. I would suggest you people to go on YouTube and check out some video how they make the mirror. It's keep on polishing, putting various of chemicals to remove any kind of roughness that's there on the surface. So now there are two things that we can do in polishing a metallic sphere. Either we can polish the inside surface of the metallic sphere. So when you polish the inner surface, then you can clearly see the inner part becomes the mirror and the outer part of the sphere is non-reflecting. So that makes it a concave mirror with reflecting side inside. What about convex? For convex, we polish it from the outside over here. So when you're polishing it from the outside, then outside is the reflecting part and the inner portion is actually the non-reflecting side. Now, since these mirrors are made from the sphere, some characteristic of that sphere get clubbed to these mirrors as well. They remain equally important, even though these mirrors are then later cut out from the actual sphere. The center of the original sphere from where it was made still is called as the center of curvature of the mirror. In both the cases, be it concave, be it convex. The radius of the original sphere from which it was made is called as radius of curvature. And then we draw a line, which is the diameter, and wherever it cuts the mirror on the circumference, that's called as the pole, a point. And pole is very important because all measurements we will be doing from pole itself. All right. So the diameter that we draw is also called as a principal axis. Important point about this principal axis, mirror is always symmetric about it, as much as they're on the top, as much as they're at the bottom. So two types of spherical mirrors we learned, concave and convex, and we learned about the characteristic of each one of them. Now moving ahead, how do we form image with these mirrors coming into play? Well, as I told you before, we simply follow the law of reflection, nothing else. So if you have a look here, whether I have concave or whether I have convex, we have certain rules to follow. The first rule that we follow, when a ray is actually coming parallel to the principal axis, it'll always pass from focus. Why is it so? Well, that is the reason why it is named as focus. Rays which are coming parallel means they are coming all the way from infinity, right? And all the rays which are coming from infinity finally get focused at a point. That's why it's named as focus. So if you keep some vessel over there with certain amount of food, then it may even get cooked. And that's how we have some kinds of solar cookers as well. Obviously, it's not just a concave, it's a combination of multiple things. But that's the principle behind it. And for convex, if you look at, the ray actually cannot pass from focus because focus of a convex lies behind it and rays cannot go behind the mirror. So it just reflects with law of reflection. And remember, here also the law of reflection is being followed. Remember, you would say, how do we know the law of reflection is still being followed? Well, you can simply have a look that the incident ray is coming parallel to the principal axis, and the reflected ray, well, that also you can clearly see. It's going like this. So this is our incident ray. This is our reflected ray. Then you might ask, where is the normal? So normal is normal to the surface. Here is the surface where it landed, the light ray. So I must draw a line that is 90 degree to it. Can you all see this dotted line? That's making a 90-degree angle. And now it becomes really interesting because if this ray is, this normal is 90 degree to the spherical circumference, any line that is perpendicular to the circumference must pass from the center. So all the normals of a spherical mirror always pass from the center of curvature. And how is the law of reflection followed? If this is our incidence angle, theta, then this is our reflection angle, theta. Both will be equal. So it is happening following the law of reflection. How it is happening in the other mirror? Well, you can simply follow this path. Like this. It falls at theta, it reflects back at theta. So law of reflection is working over here as well. So moving ahead to the next rule. So remember, in convex, the rays are not meeting at the focus. Rather, it's just appearing to be meeting at the focus. So you can clearly by now must have an idea that in convex mirror, virtual image is forming. Because that's what I told you about virtual image. It appears to be forming there. In reality, it's not. And in concave, later on we'll see that it can form both real and virtual. You can form virtual image with concave also. Not necessarily that only convex can do that. But yeah, when you talk about convex, it only forms virtual image. It cannot form real image. That's a very important point. Convex mirrors never form a real image, while concave can do both. We'll see later how. Coming back to the rule, now moving ahead to the rule number 2. What if the ray is incidented at the focus? How it's different from the previous? In previous case, ray was coming parallel and then passing from focus. Now it's coming at focus, and so it's vice versa. It will become parallel to the principal axis. Exact reverse of the previous scenario. All right. Moving ahead, rule number 4, and that is, what if the ray falls at the pole itself? Well, now the principal axis is itself the normal, 90 degrees. So actually, the angle it will make, the ray with the principal axis, becomes the incidence angle. And then you know, according to law of reflection, if this is theta, this has to be theta. So ray actually passes symmetrically, isn't it? It makes the same angle with the principal axis. So whenever rays fall directly at the pole, it passes by making the same angle. If this is theta, this has to be theta. Now, keeping these rules in mind, you can always, form the ray diagrams of the mirror. One more important, point I would like to add here. What if, like, I think I missed rule number 3, and that point I would like to mention here. And that point is, what if the ray is passing from the center itself? If here is the center of the mirror, what if passes from the center? So if it is passing from the center, think about it. It's already falling at 90 degrees to the mirror. And whenever a ray falls at 90 degrees to the mirror, that means incident ray and normal are parallel to each other. They are coinciding. If incident ray is parallel to the normal, its incidence angle is 0. So what must be reflection angle? It must also be 0. That means the reflected ray must also be parallel. It must just come back like this, retrace its path. So very important point you learned here. If the ray passes from the center, then it retraces its path. How we will show the same in convex. In convex, I can show it like this. Here is the center behind. So the ray will only appear to be falling at the center like this. And since it has fallen at 90 degrees, it will just reflect back. So rays retrace their path when they fall at the center. Very important point to notice. So having all these rules in mind, we can now form the ray diagrams. So what we'll be doing, keeping objects at various distances and see how the image can appear. First, you can see in the diagram A, we can see that the image is actually at the infinity. So what will happen if the image is at infinity? The rays will come parallel like this. And we have just now learned the rule. If ray come parallel, it pass from the focus. So the ray will also come and pass from the focus. So a real image would be formed at the focus, as all of you can see. So everybody is able to understand that a real image will be forming at the focus in this case. So next, what if image is not at infinity, but at certain distance from the center? So in this case, again, it will come parallel. Just a So again, the ray is coming parallel, and then it will just pass from the focus like this, as usual, the rule. And look at the other ray that they've taken. Now this is something new. The other ray is actually incidented at the center. And what did I tell you? If a ray passes from the center, after hitting the mirror, you can see it just rises back along the same line. It just passes by here, and then you see an image formation over here. Since this image is forming with the rays actually meeting there, you can see it will be a real image. Did you all follow this? It'll be a real image. Moving ahead to the next one. Again, the image, the ray is coming like this, parallel, passing from the focus. Again, it's coming like this, passing from the focus. And finally, you see an image formation here. This is a very interesting case because here you have kept the object at the center. And the geometry is as such that the image also forms at the center. And that too of equal size. No difference. Moving ahead, what if you come between center and focus? Again, follow the same rule. One ray parallel to the axis, follows, passes from the focus. Other ray hitting the head of the object and then passing from the center. It will just retrace like this. So rays actually meet behind the center. So in this case, again, the image is real, but behind. Last case, when you put at the focus, is again a very interesting case. First ray, as usual, you see, in every diagram, I'm doing the same rule again and again. First rule is always ray parallel to principal axis, passing from focus. Other is from the head that goes from the center. Again, due to symmetry, these two rays will become parallel to each other. And if rays are parallel to each other, they won't meet. Or in mathematics language, we say they meet at infinity. So we say the final image is forming at infinity, very far away. And what about the last? Well, in last case, see, we have moved it between pole and focus. Object is inside the focus. So now when you draw the ray diagram, first ray I have taken, you can see falling at the pole, and we remember a rule. When it falls at the pole, it passes symmetrically. And the other one, which is at the head of the object and going from the center, just retraces its path. Now see, if we look at the reflected ray from the mirrors, both are actually diverging. There is no chance that they can ever meet. They just keep on getting diverged. More and more distance will keep on increasing between them. So the only way we can see image here is extended behind like this. And when you extend it behind, it appears to be coming from a point behind. So that is where the image is formed. So this is the point where I can say that even a concave mirror can form virtual image. But what is the condition for that? The condition for that is that the object must be between focus and pole. Then only the virtual image can be formed. So here I can write, first case also it was real. In the second case, it was also real. Here, real as well. Here, real as well. And although here it's forming at infinity, but still some image is forming in front of the mirror only. So we still call it real. But the last case, it's forming behind the mirror. So we call it virtual image. You can also see the size of the image versus object. In first case, the image will be a point image. So we say diminished. The image is diminished. In the second case, well, first of all, it's inverted. That's first thing. And second thing is, you can see the size is smaller. So whenever image is of smaller size, we say it's diminished. You won't even be able to observe the image properly. In this case, it's very interesting. It's although inverted, but of same size. In this case, well, real, inverted again, but magnified because the size increased. In last case, it will be magnified because when forming at infinity, it will be pretty enlarged image, right? And inverted also. So I would write here inverted and enlarged, magnified as we call it. In last case, virtual. Well, first of all, it's erect. Image is in the same orientation as object. There is no inversion. And the other thing is it's magnified. Now, if you feel what all things have been told, how do I remember this? Well, see a practical example. You just pick up a spoon and you can see when you face the spoon with the curved part like this facing towards you, then it is a concave mirror. So you just watch spoon like this and do one thing. First of all, keep the spoon far away. That will be like rays coming from infinity, the first case. And you will see your point image in the spoon. You will appear almost like a dot. In the second case, bring it a little close to you. That will be the case number B. And you will find yourself upside down in the spoon. You can check that even now. You can run and bring a spoon right now. Pause this video. So if you are having it right now, then you must be looking at, you seem to be inverted. Then you move it close. Keep on moving it closer. It will still be inverted, but the size will gradually be rising because in the case number B, when it is far, the image is very diminished. When you bring it to the center, its size is increasing. And now, when you further keep on moving it closer and closer, size is increasing. You go to case number C, then you go to case number D, size is increasing. And then suddenly you will going to pass the focus. The moment you will pass the focus of that spoon, then you will directly jump to case number F. In that case, suddenly you will see yourself upside, same as the orientation of yours, a perfect erect image, because then you jump to the case number F. How do we see the same thing in convex mirror? So here is the convex mirror. In convex, we don't have multiple cases. It's just one and the simple thing. First ray again going parallel to the principal axis and then reflecting, as all of you can see. And after reflecting, what is happening to it? We extend it behind and it appears to be going from the center. The second is directly incidented at the center. So after reflection, it just retraces its path like this. So in reality, these two rays will going to diverge. Finally, the ray is coming like this. This ray is going like this. There's no way they can meet ever. They keep on diverging. So we extend them backward. And in this extension, we find them meeting over here. This was, by the way, the normal, the other one which I had drawn. That's the normal. You can see it comes at theta angle. It reflects at theta angle. So finally, we get a very tiny image here. Compared to object size, image is very diminished. So first of all, it's virtual. A convex mirror can only form virtual, and that too diminished. Right? So that's about the convex. Now, there's a question for you all. Just see to it, read it. So you've read it, that a concave mirror is there. Its focal length is given. You want a virtual image from a concave mirror. It becomes pretty easy because there is only one case when concave mirror forms virtual image. Which case was that? When you actually shift object between pole and focus, remember? So you can just see which distance is lesser than 15 because you want it inside focal length. So A option. So our answer should be A. Easy. Second question. Two big mirrors A and B are fitted side by side on a wall. A man is standing at such a distance from the wall that he can see the erect image of his face in both mirrors. When the man starts walking towards the mirror, he finds that the size of his image in mirror A goes on increasing, but that in the mirror B remains same. See, it becomes pretty easy with one case, that if you talk about the mirror B, his size is not increasing. In the mirror B, it remains same. So you may walk close and away from a certain mirror, but your size never changes. And which mirror is that? Plane mirror is that, isn't it? So mirror B is plane mirror. And very easy it becomes for us because only one option is there with mirror B as plane. So our problem is solved. But we can also check for mirror A. Just see what they are saying about mirror A. When the man starts walking towards the mirror, he finds that the size of the mirror, size of his face in mirror A goes on increasing. That's what we observed also. When you move closer towards a concave mirror, you can see initially it was diminished, but then you can see it kept on getting magnified and enlarged, isn't it? So it has to be the C option. All right. So another question. Okay, I'm so sorry. That has to be from a lens. So let's do one thing. We will put this question once again when we will do the topic of lens, but you can save it. So I think today, when it comes to spherical mirrors, this much is sufficient, right? So thank you very much. See you in the next lecture.